Bismillahirrahmanirrahim. Assalamu alaikum. Today what we're going to learn is how to work with current and voltage inside of resistors. So that previous lesson kind of helped you understand a lot of the components and how they look like in a circuit. And today we're going to get into making those circuits and the two particular kinds of arrangements that you need to know. All right. So the first thing that you got to know is a famous law in electricity, and it's called Ohm's law. And Ohm's law says that the voltage is equal to the current multiplied by the resistance, and that's for every single resistor and every single battery. That's for every single circuit. All right. So let me explain to you what that means exactly. So I'm going to go here, and what you have is it's kind of like the F is equal to ma of electricity. Think of it that way. Okay. So basically, this what I have in the red is a resistor. Recall that, if you think of sand particles inside of a hose, it really helps to understand what resistance is. So the current that is running through this resistor, right? The current that's running through this resistor, and we'll talk about current in a moment too, is running at 9 milliamperes. Okay, amperes is the units that we measure current in, and milli, it's a relatively small number. So it's a little bit of current that's running through it. And we've done this for so many different concepts in physics this year. But if you look at the resistance is really large. And what ends up happening, right, is the voltage is actually equal to I times R. And so what you'll notice here is you need 3 such batteries, right? You need 3 1.5 volt batteries to push those charges across that resistor, right? If there was less resistance, the battery wouldn't need to be so strong. All right, so what I can do here is I can say, okay, what if I were to make the resistance? Notice how you can't toggle the current, right? You can't toggle the current. The two things you can toggle is either the voltage of the batteries or the resistance of this resistor right here. So let me take this resistance and let me make it a little bit lesser. All right, so let me make this resistance a little bit less. So as I'm making it less, notice how the particles inside, they're disappearing. And so as we make that resistance less and less, right, notice how the current becomes larger and larger, right? And it should make sense that if you're decreasing the amount of impediment to the flow of those electrons, right? We'll come to learn that electrons actually flow the other way, but for now, right? What we discover is now the voltage stays the same, but the current running through that wire is actually much higher. All right. And finally, what if what we did is we reset this and we just put in more powerful batteries, right? Let's suppose that we put in more voltage across this. So let's increase the voltage and observe what would happen. So if I increase the voltage across this and I put in twice the amount of batteries, notice how the current goes up, but not as proportionally as before, right? You need a lot more voltage to push across that current. So it's a lot easier to make resistors than to keep putting, because it's expensive to put more and more batteries, right? So now if I decrease that voltage, right, notice how the current that's running through here is relatively small. All right, so that's that first rule that you need to learn, called V is equal to IR, that says that the voltage that is across a resistor is equal to the current across the resistor multiplied by the resistance of the resistor itself. Like, that's an actual rating. Now you'll notice a few things. You'll notice that voltage is measured in V, or volts. Resistance is measured in omega, which is called ohms, right? And that's where we got Ohm's law from. And current is measured in amperes. That's the letter A. And then that says milliamperes. Okay, so just kind of understand this idea, and I've linked this as well in our lesson notes, just so you to start understand what V equals IR stands for. Okay, now the next thing that we're going to do is we're going to tie it in with a different equation that is not in your book, but you do need it, and this is called the power equation. So the power equation you generally want to know how much power is across every single resistor in a circuit. And the way that you can do that is you can take many of the same recipes as Ohm's law, and you can go ahead. So you want to put both of these on your blue sheet. You want to multiply the current times the voltage. So if you take the current and the voltage, or I and V, and you multiply them, you'll end up with power. Now you may be thinking, where did you get this equation, the second one, and where did you get the third one? Well, basically, they're just reiterations of the same equation. It's just we're thinking to ourselves, well, if V is equal to IR and P is equal to IV, then technically speaking, P is equal to I times IR because I substituted in for the V. So that becomes I squared R. And that's how we got that second definition. And the third definition, it's basically the same thing, but this time you make the connection that if V is equal to IR, then I is equal to V over R. And therefore, this equation can also be written as when we say P equals IV, we can write down V over R times V, which becomes V squared over R. And that's how we got that second one, and this is how we got that first one. Okay? Now, we'll come more to these eventually. So even if you're not quite wrapping your mind around it, that's fine. Just go ahead and jot these down and understand that P stands for power, I stands for current, V stands for voltage, and R stands for resistance. The things that you can control are basically your voltage by putting in more batteries, or your resistance by increasing the amount of resistance within a resistor. All right? Now, I'm going to show you guys two types of circuits that you need to learn in this course. One of them is called a series circuit, and one of them is called a parallel circuit. All right? So in a series circuit, basically what happens is, think of it this way. Think of a battery pump, all right? And what it's doing is, sorry, a pump, and what it's doing is it's increasing the potential energy of those charges to actually do work, right? So that's what the battery is doing. And so think of this as like that pump, right? Now, what happens is those charges start to go around the circuit, and as soon as they meet that first resistor, right, as soon as they meet that first resistor, this water wheel, it actually starts to turn. And so as far as the potential of those charges is concerned, now they have less potential to do work because they dissipated some of that work within this water wheel right here. They help to turn that water wheel so they have less energy, right? Think of that, what the battery is sending out is energy. So now they are at a lower level of energy. Then they go through the second resistor and they're even at lower energy. And when they come back to this terminal of the battery, right? They come back to this terminal of the battery, you discover that now they have zero charge. And what is the battery's job is it pushes those charges back up. And that's why the battery drains out. Now you might be wondering, wait, so is it always going to happen that you're always going to end up at zero by the time you come back? Yes, absolutely. That it just depends on what you make the battery and what you make the resistors. The resistors will accordingly use as much as the battery sends out. You understand? Right? So if the battery's not sending out much, these are just going to move slower and they're going to go through the same things, but they're not going to go as fast once off. And other thing is they're most likely not going to make much work happen for that water wheel. And technically speaking, if your battery gets really weak, then it won't be able to push those charges up and then through that circuit, and that's why the circuit dies out. All right? So that's the first example. And I want you to think of this next time you see a series circuit. So we say that this resistor is in series with that resistor. And the reason why we say that is because they are along the same path. There's only one path between resistor 1 and resistor 2. All right. So this is called a series circuit. All right. Now, what is a parallel circuit? In a parallel circuit, first off, let's just take a look at a picture of what a series circuit then looks like. Is you got the battery right here, and the battery actually sends out electrons from the negative end of that terminal. Okay, so the electron flow, this was so confusing to me when I first learned this. I'm like, wait, so we've been drawing this all wrong the whole time. So the 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 electrons are being pushed out from the negative end of the terminal, and what ends up happening is they are attracted to the positive end of the terminal. So actually the electron flow is this way, the way that I'm moving my arrow. It's actually this way. But what we call electron flow is one thing, and what we call conventional current is the other way. So when you saw in this previous diagram that they were showing you these positive charges, this is called the conventional current. This is the conventional current, even though technically speaking, electrons flow the other way through this terminal. All right, I know that that's not the best way to start the lesson. It's kind of confusing, but I'll try to explain that to you a little bit further in a little bit more detail soon. Now, so here's what happens. As these electrons flow through, what happens is they encounter resistor number one, so that right there is a resistor, and then they encounter resistor number two, and then by the time they come back to the battery, they have lost all their potential to do much because the resistors have taken up all of that charge, right? Now you might be wondering, what does a resistor do then? So that's where it's very useful to think of a resistor in terms of power. Many times that resistor isn't just a pure resistor, it's there to do something, right? Many times it's a light bulb. So the light bulb is going to light up when the current runs through it. So think of it that way. And I do have an app for you in a little bit that I'll show to you. Now, one thing that you want to keep track of is as the current is moving through in a series circuit, all right? In a series circuit, basically what happens is the current is the same, all right? The current is the same. Now, once again, this is through a series circuit, all right? So the current that, if you want to call that current I, as it runs through this resistor, it's the same exact rating as it runs through the other resistor, all right? It's the same amount of current because there's really, if you think about it, there's only one pathway for the current to follow, all right? So the current is the same that's felt by both resistors. However, the voltage, you can calculate it by doing V is equal to IR, all right? So you take the current and you take the resistance rating, you multiply them, and you'll find out how much voltage goes through each one of these resistors. Now you might be thinking, I thought the voltage of the battery is all that runs through them. No, not true. Okay, that's what I used to think as well. But as we talked about in this analogy, there's a potential, right? So that's, think of it as voltage. So there's a potential and there's a certain amount of voltage drop that occurs between each one of those resistors. And that can only be calculated by you figuring out how much resistance do you actually have in the circuit. And I'll be making this for you in a moment. So again, I will explain the same concept to you. Now, the other kind of circuit that you can have is called a parallel circuit. Okay, so a parallel circuit. And you may take a look at it. Literally, they look like they're parallel. But what's so specific about a parallel circuit is the current can split up. There's a juncture where if you're looking at those electron flow, right? If you're looking at the electron flow and it's going this way, all right, let's just assume that we're looking at the electrons. So as it's going this way, over here, that electron flow splits. Okay, it splits. And so one end goes that way and one end goes this way. And so in this case, what happens is the current is not the same because it just split. And when I say the current's not the same, it's not the same through each one of the resistors. So what really is the same is actually, it turns out the voltage is the same that's felt by both of those resistors, but the current, you need to figure it out using I is equal to V over R. Realize that that's basically the same equation as V equals IR, just been restructured, okay? So that's the big deal about it. Now, here's what's interesting. After some time, what happens is the current doesn't die, so the current, it rejoins, all right? It rejoins right here. It rejoins, and then it just continues where it was before. So if you had a current of like let's suppose 10 amperes is going to split into a certain amount here and a certain amount there, depending on how much resistance is on each one of these resistors. All right. So now let me show you kind of how this looks, because parallel circuits tend to confuse students a lot. So think of an analogy here. Same exact battery, right? Same exact battery. Now, what it does is it pushes those charges, and as those charges are going, notice that this time the charges don't have one pathway to follow. So these charges can go down pathway number 1, which is, let's call it the way of resistor 1, or they can continue in this direction and then go down pathway number 3. You see that? So pathway number 2, where this is resistor 3 sitting here. So as they go down, right, as they go down, think of these water wheels. Notice how these two water wheels, they're turning very slow, right? R1 and R3, they're turning very slow. But R1 and R2, sorry, they're turning very slow, but R3 is turning very fast, right? So why is that exactly? Well, what happens is in that previous, we learned that basically initially they're going to have a bunch of current, right? They're going to have a bunch of potential, and they're going to run through each one of these water wheels. And as they go through those water wheels, they're going to lose their potential. Well, that's when they were in series. So notice how in this scenario, what's really happening is the R1 and R3, they're parallel, okay? Not because they're physically parallel to one another, but because you can go through a different pathway at that juncture, and therefore you can go through R1 or you can go through R3. That makes them two parallel. But notice that the relationship between R1 and R2 is that they're in series between R1. Let's suppose you were at R1. The only way that you could move on in this circuit is to continue through R2. So we say that R1 and R2 are actually in series, whereas R1 and R3 are considered to be in parallel in that sense, right? But what we're trying to say here is this. Notice that that potential, it drops the certain amount, right? All the entire amount, the voltage is completely dropped right over here. Whereas in that second scenario, it actually drops a little bit, then it drops completely. And that's always going to happen. All right. This is something that confuses students a lot. They're like, wait, so the voltage is always going to be the same going through both? Yes, through that end and through that end. The voltage that it dissipates here is going to be the same as the voltage that dissipates here. And again, I will give you more examples of this in just a moment. Now, let's actually make a circuit, okay, just to help you understand this concept. So I've said a bunch of things to you that I'm quite sure some of them aren't quite making sense to you right now. Okay, so here's what we generally begin with. We begin with a battery. Okay, we begin with a battery, and then we take a piece of wire. Okay, so you're going to eventually do some kind of a activity on this, and you'll find out about that eventually. But we have a, a an amount of wire, and you're welcome to play with this. I've linked this in your lesson on the website. So you have some wire, and to this wire, I'm going to go ahead and connect a couple of resistors. Okay, so here is a resistor. Let's just make a simple circuit here, and I'm going to go ahead and connect these wires like this, and so you'll see that the electrons are flowing through that resistor. All right. And notice how the electrons are flowing out through the negative terminal and they're coming back in through the positive terminal, right? But that's not the conventional way that we represent it. So the way we represent current is the other way, okay? So now notice how that red arrow, those red arrows are flowing through that resistor, and then they're coming back through the negative terminal of the battery. So that's the one you want to understand a little bit better, okay? Now, one thing that you'll notice is if I click on these values over here, right? If I click on these values over here, you can tell that this is a 9-volt battery, which can be changed if you want, and that is a 10 ohm resistor, all right? Now, let's break this circuit, all right? Let's break this circuit, and let's do something else with it. Now what we'll do is we'll connect another resistor. All right, we'll connect another resistor like this. And once we connect that resistor, we're going to connect some wire. And they don't have to be exact rectangles, by the way. So you want to make it look like this and just get rid of this piece of wire. that's fine. Okay, so we just try to make it look like rectangles so people don't get confused. All right. Now notice how the current is running through, but it seems to be running a little bit slower than before, right? If you observe what it was running like before. But more than that, you can tell how much voltage is going to be going through each one of these and how much current is going to be going through each one of these as well. And that's what we're going to be learning today. All right. Whereas on the other hand, the other one that I drew for you, that is a parallel circuit, very similar, except that now there's two pathways for current to travel. Now, you're not going to be drawing fancy looking batteries and fancy resistors when you do this lesson, or the homework. You're going to do a lot of diagrams in this lesson and the last lesson of this course. So what really happens is we represent, even this is not the most valid depiction, so let me just go to the original. If you click on this button right here, this is how you generally draw your current, and your battery looks like that. Let me shut off the values. All right, your resistors look like zigzags, and then you draw just one arrow or a couple of arrows showing which way the current, the conventional current once again, is flowing. Notice how the positive terminal is larger and the negative terminal is smaller in a circuit. Okay, you're welcome to play around with it and get used to it, but we're going to go ahead and move on with the lesson. So now we're going to talk about how do you actually solve these. All right, how do you actually figure out how much is going through each one of them. Now there's a lot of ways to do this, a lot of descriptions that teachers have given, but I will be giving you basic rules here. Okay, so if you have resistors in series, first off, what is a resistor in series? A resistor in series is where you only have a single pathway. All right, there's only a single pathway between that battery and that resistor. Okay, so single pathway is what we're talking about here. Whereas a resistor is in parallel, there is multiple pathways. You can say dual pathways. All right, for the sake of your course, there's dual pathways that current can flow. So that's your first understanding of series and parallel, right? It takes a little bit more to understand it, but inshallah, in due time, we'll cover that too. Now, what you want to remember is resistors in series to find what we call the equivalent resistance. All right, REQ is called equivalent resistance. The way that you get equivalent resistance is you have to add up all of the ratings on the resistors. So if one resistor is 10 ohms and the other one is 10 ohms, you add them up and say the equivalent resistance, some people call it total resistance, in that entire circuit is going to be 20 ohms, like that. Whereas the current, all right, the I, it refers to total current. All right, that's called total current. And the total current in a series circuit is the same as the current running through every single one of those resistors. Now, if you were in parallel, there is a slightly different way to do it, and we'll come to covering that when I actually come to an example. But it's basically now switching up the idea, and we'll see how that happens in just a moment. All right. But just to give you a little bit more substance on this before I go into some mathematical examples, basically, suppose you had a battery, right, and it's connected to two light bulbs. Well, both of these light bulbs are receiving a certain amount of voltage, right? And what happens is you treat those light bulbs as resistors. That's what I was trying to explain to you. So power is brightness, right? So you want to look at the power rating on each one of these to figure out how much power is each bulb getting, right? So in a series circuit, notice how if you were to cut any piece of the wire, right? Let's suppose one of these light bulbs were to go out, right? Look at this diagram down here. All the elements need to conduct. If even one of the elements breaks, the entire connection is broken. All right, the entire connection is broken. It's as good as you just snipping the wire here. And now none of the bulbs are going to get any current, right? Whereas in a parallel circuit, one of the benefits of having dual pathways, if I take this picture right here and I make it a little bit larger if I could, I guess not, but basically what happens is that current, if let's suppose you were to cut the wire here, all that current can still flow through that second resistor. And so things like Christmas lights and stuff like that, they're wired in this manner because that way, in case one of them blows out, let's suppose that bulb number 2 blows out, it's okay. That current can still continue to flow through that piece of the wire. There's nothing that's cutting that wire. All right. So more on that as well, inshallah, in a little bit. All right. So let's go ahead and try some examples. All of these rules are going to make a lot more sense when you actually try some of the examples. So I've copied the first example here because it requires that you also make a diagram, which you're going to be required to draw diagrams as well. So it says sample problem A, resistor in series. It says there is a 9-volt battery and it's connected to 4 light bulbs as shown at right. Okay, so we're going to give these light bulbs, we're going to give them labels. Okay, so we're going to call this light bulb A, light bulb B, light bulb C, and light bulb D. All right. Now, here is how you represent this diagram. All right, here's how you represent this picture as a diagram. Basically, what you begin with is you say, okay, I've got a battery. Okay, so I've got a battery, and I'll make a positive terminal on the right, a negative terminal on the left. If you wish to do it the other way, that's perfectly fine. Now, what I'm saying is the current is going to flow out from that battery. So here is my circuit, all right, and it's going to go to that first bulb. All right, so when it goes to the first bulb, I'm going to draw that resistor like this. Then it goes to the second bulb, so I'm going to draw that resistor like that. All right, these drawings are they're pretty broad. You could do them in many different ways, but as long as you got that idea down, right, and like the current is flowing from one point to another, and then it's going to come back around, right? It's going to come back around. Let me make that a little bit more straight. And it's going to go through another resistor, and then it's going to go through another resistor, right? And then it's going to flow back to the battery. All right, let me just erase some parts of it, and you're welcome to continue to draw these as well. So how am I going to depict this? I'll say that it goes, actually, you know what? If I wanted to alphabetize this, why don't I do it this way? Just to prevent from confusing anybody. Let's make the current flow the other way. That way it's alphabetical to what I had said earlier. So let's make the current flow the other way. Okay, so that's all I need to do. Okay, now first understand that it's going to first go to the 2 ohm resistor, okay, which is the resistor A. So the resistor rating on that first one is, so resistor A, so R sub A is equal to 2 ohms, like that, all right? Then resistor B is 4 ohms. So I'm going to go to resistor B, and I'm going to label that as 4 ohms, all right? Then it's going to flow to resistor C, which is 5 ohms, and the last one is 7 ohms. So resistor C is 5 ohms, like that, and resistor D is 7 ohms. So notice that the bulbs behave like resistors, all right? Now let's just take the insides here because we're going to be needing that space most likely to solve some things. And I've just simply put the resistances outside. Okay, so the resistors, look at, it's not really a work of art. Actually, it's not a work of art at all. But the whole point is you just need to make zigzags on that circuit, 3 preferably, to show what's happening. So here's the conventional current, okay? The current is going to flow out through here, all right? So let's call that current I. All right, that's current I. And then it's going to go through the first resistor. Think of the water wheel and the charges going through the water wheel, okay? So it's going to go through that first resistor. Now, what you want to do is you want to figure out how much exact voltage is going to drop through here. Because one thing that we haven't listed yet is the 9 volts. Okay, so there's a 9-volt battery that's pushing all of these charges. So how much of that voltage is going to drop through here? So here is the logic. The logic is if I can figure out how much current I have, then I'll take the current and I'll plug it into Ohm's law, and I'll have the amount of voltage that drops through that first resistor. In other words, I'm trying to figure out what the voltage drop across A is. Okay, and books call it the potential difference, but I like to call it the voltage drop because literally, if you think of those charges dropping in potential energy as they move through, it makes a lot more sense. Okay, and then let's just complete the circuit, and then we'll get into the calculations. That same current. All right, the current's going to be the same. It's the same exact amount of current. It doesn't go anywhere. It then continues through the 4 ohm resistor. Then it continues along the circuit, and it continues along this resistor, and then this resistor, and finally that current comes back to the battery. All right. However, the voltage is what drops as we go through. Please understand that. It takes a while to get used to that. So how do you actually work with this? Step number 1, the first thing that you need to do is you need to find all right, so let me label this. So step 1, you need to find Req, all right? And that's called equivalent resistance, as I told you earlier. So you got to figure out what's the formula, all right? When things are in series, how do you work with resistance? So for that, I've conveniently placed for you again that same exact formula right here. It says whenever you see resistors are in series, you're supposed to add up the resistances of each one of those resistors. All right, so I'm going to go here and I'm going to add up the resistances of each one of those resistors. And so I really have Req, all right, Req is equal to RA plus RB plus RC plus RD. Why are we doing it that way? Is because they are all in series, so it's like one big resistor. Think of it that way. That's been chopped up into 4 pieces. So when we add all those numbers up, we're going to end up with 2 plus 4 is 6, plus 5 is 11, plus 7 is 18. So the equivalent resistance is 18 ohms. Now, what do you do with that equivalent resistance? So this is step number 2. After you find the equivalent resistance is equal to 18 ohms, then what you do is you use Ohm's law. All right, you use Ohm's law, and you're using Ohm's law to find I. You want to find the current that is running through each one of these. All right, so Ohm's law says V is equal to IR. Well, now what we can do, bismillah, is we can shuffle this around and we can say I is equal to V over R, like that. So if I is equal to V over R, the battery's voltage was 9 volts, all right? And so what we know is 9 volts divided by, bismillah, 18 ohms, because that's the equivalent resistance right there, is going to give you 0.5, and the units on this are amperes. Okay, so some people call it amps. So we end up with I total, right? The total current running through this circuit is going to be 0.5 amperes. All right, so take a look at these values. If you're getting confused between what's the difference between Req and RA, RB, RC, Req accounts for all of those and treats them as one resistor. So what we generally do to help students understand this is, what do we mean by 18 ohms as the equivalent resistance? What that really stands for is this, okay? It really means pretend there was only one battery, okay, as there is right now, and there was only one resistor that was in series with the battery. That Req would be 18 ohms. That's what we're trying to say. We're basically treating all 4 of those resistors into one resistor, right? Just pretending like it's so that we can get an equivalent resistance. So that's the amount of resistance in the entire circuit. And then you use that in Ohm's law to actually go ahead and solve for the amount of current, and that total current represents how much current is running through that resistor, by the way. All right. Now, let's go to rule number 2. Rule number 2, so this was rule number 1, and we used it for a certain reason. We used it to find the equivalent resistance. Rule number 2 says that the current in series, so I said this to you earlier, I'm saying it to you again. The current in series resistors that are wired in series, is going to be the same. So for instance, bulbs A, B, C, and D, they feel the same amount of current running through them. Do you understand? All right. So what I'm trying to imply here is because each one of these has the same amount of current running through them, because they are all in series, what I'm going to do here is I'm going to go to each one of them and I'm going to write down that the current running through the first resistor is equal to 0.5 amperes. The current running through the second resistor is also 0.5 amperes. Notice how it doesn't matter what the resistor is anymore. It's all about the fact that they're in series. Because they're in series, you just go to every single resistor and you say that the current running through each one of them is 0.5 amperes, like this. Okay, now the last thing that we do is we calculate voltage, all right? And again, to calculate voltage, this is the most important formula. Notice how we use this formula back in step number 2 to find us the total amount of current. Now we're using the formula again because we want to figure out how much voltage drops through each one of these. If you don't understand what I'm saying, right, I totally get that. In the beginning, this is a lot to handle. So again, these charges are moving through, right? But notice how there was a certain drop in potential of those charges when it went through each resistor, but it depends on how much that resistor is. So what we're doing is we're trying to figure out how much voltage drops across each one of these resistors, all right? So to do that, right, the theory is kind of difficult, but the equation is very simple. To find the voltage drop through A. Now the notations are very important. Please notice that I wrote down V sub A. Don't confuse V sub A with V, because when you say V, you're referring to the battery. The battery is the only one that can be referred to as V, all right? So V sub A is equal to I sub A times R sub A. And that essentially means you multiply the 0.5 and the 2, and you end up with 1. So the amount of voltage drop through that first one is 1 volt. So you lose, think of it this way, you lost 1 volt right there. All right, 1 volt was dropped here. Now let me remind you, we started off with 9 volts. So how many volts do we have left? We have 8 more to go. Okay, so we have 8 more that are going to go through this circuit. Now, let's go to the second one. The second one is voltage through B is equal to the current through B times the resistance through B. And again, all that means is you just take those numbers, so 0.5, and you multiply it to 4, and you end up with 2 volts. So now you lose from that 8 that was left over, you lost 2 more voltage right over here. All right? So, and we continue through this circuit. All right, now VC. VC, once again, is IC, RC, and that's 0.5 times 5. So now how much did you drop? It's a 2.5 voltage drop. So you lost 2.5 volts. Now, many students can make that connection at this stage. They'd be like, wait, so you're saying you started with 9, you lost 1, so you got 8 left, then lost 2, so you got 6 left, then lost 2.5, that you got 3.5 left. So shouldn't this be 3.5 that you lose? And it's a really good way to make sure that you're doing it right. Notice how V sub D is equal to I sub D times R sub D, which is equal to 3.5 volts. And so as I showed you in that picture of the water wheel, by the time that current comes back, remember, it's not the voltage that flows, the voltage drops, right? The voltage drops. It's the potential that we think of as the voltage. But the current is what's flowing. But by the time you come back to the battery, by the time the current has come back to the battery, it's lost all of its potential to do work. It's not like we're losing electrons off the wire. Please understand that, okay? The electrons are still flowing. It's the same number of electrons, but their ability to do work has gotten less. Just like we're in the month of Ramadan right now, and then when you start the day, you have some energy to do work. It's the same you, but by the end of the day, you have less and less energy. Sort of think of it that way, okay? All right, so that right there is a series circuit, and that's how you work with the series circuit. So as far as step 3 is concerned, in step 3, basically what you got to do is you need to go through each one of them and use Ohm's law again, right? So use Ohm's law again, all right, and to find each one of the voltage drops, to find voltage drops. Now, in the book, they often use the words potential difference, and they actually use that word a lot more. In fact, I'm not sure if they even use voltage drops too much because I do use different textbooks to prepare for my lessons. So, potential difference is better known as voltage in this situation. Now, one last thing that we're going to do here with this circuit, and then we move on to another one, is we're going to calculate the amount of power, the amount of brightness that's going to be in every single bulb. And the way that you can do that is it's not much more. All you got to do is you got to take the current, so P is equal to IV, all right? And that's not 1V, that's IV, that's current. Let me put an I on it, all right? That's current times voltage. So the power through that first bulb, okay, let's write it this way. The power through that first bulb is going to be P sub A is equal to I sub A V sub A. Now what is I sub A, right? The current is 0.5. And what is V sub A? The voltage drop was 1 volt. So 0.5 times 1 is going to give you 0.5 watts. All right, so 0.5 watts. So this bulb is going to have a certain amount of brightness. All right, so power and brightness, they're proportional to one another. Now, we'll go to the next bulb. All right, we go to the next bulb, the one that's considered the 4 ohm resistor. And so for this one, let me calculate it up here. So power through B is going to be IB VB, right? And so that is going to be 0.5 times 2, which again gives you the same amount of, one sec, yeah, it gives you a little bit higher. So you end up with 0.5 times 2, and so this is 1 watt. So that's 1 watt of power that bulb is receiving. And so like this, you can continue through that circuit and just multiply I and V, and you'll find the resistance in each one of them. Okay, now what we're going to do, I know that first one takes a while because you're learning so much, is look at the question. It had said find the equivalent resistance for the circuit and the current in the circuit. So what the question is asking you is far less than what I taught you, because I taught you how much voltage runs through each one of them. The standard of this course is beyond the standard of the book. So you do need to know how much voltage runs through each one of them. So this set that I've given to you, this is very important, all right, and try to understand how I went through it. But basically, it all began with these rules that I've established on the right-hand side over here, okay? Now, that last one rule, notice how it says that voltage must be solved for using the loop rule. That loop rule basically says that all of that potential difference is going to come down to a 0, all right? Now, this rule is not that relevant right now, and it will become in 11.3. I'm going to leave this rule here, though, okay? I'm going to leave this here. But in 11.3, when you have a combination, then you're going to need to know that rule. So for now, rule number 3 is not very relevant, okay? Rules 1 and 2 were sufficient to get the job done for us. Okay, now we're going to try the same exact problem, but we're going to take those same bulbs and we're going to wire them in parallel. Okay, so this time we're going to have to give them those same exact labels. So I'm going to call this one at the back A, then this one over here B, then this one C, and this one right here D, and that is your 9-volt battery. Okay. Now, what is the circuit going to look like for this? Now, part of your learning is to be able to draw these. All right. So let's draw a circuit to represent this situation. Well, first off, I'm going to begin with, once again, a battery. Okay, and because I made current flow towards the left, I'm going to make it do the same thing here. Now, what happens in a parallel, look at how those bulbs were wired. Notice how the charge can go down this wire and it can go down that wire. And then it's connected to the next wire, and that's connected to the next wire. So there is technically 2 ways for current to flow. If you don't understand, how do you exactly mean there's 2 ways to current to flow? Well, think of it this way, all right? Think of it this way. All right, we're really zooming into that picture so you understand it. So current is flowing through that wire, right? It continues to flow through that wire. Now, when it hits this juncture, the current can flow here and it can flow across that other wire. So we need to represent that as a diagram. Let me show that to you again. But let's look at the back end of it, okay? At the back end, the current shows up over here, right? Certain amount of current shows up at that juncture. So some of that current will continue through that bulb and it'll just go to that next bulb, right? However, the other, it can also get broken up and then follow this pathway over here. Now remember, the bulb has a conductor on it, so the current can switch up and it can go this way, right? So now when you look at these pathways, you'll start to realize that what's really happening is actually you have a parallel circuit, and it's not necessarily because they look parallel. I just want you to realize I used to think that forever. I'm like, oh, they have to look like parallel lines. Well, they could look like anything, but what really makes a parallel is the fact that there's multiple ways for that current to actually flow. All right. Now, I'm going to just kind of space these apart a little bit because we do need that space to be working with them, inshallah. All right, so let's draw the first one. All right, let's draw the first one. I'm going to draw the first one right over here. Okay, and then back to the battery. All I'm trying to say is that is your bulb D. All right, that's bulb D right there. And bulb D, let's just put R sub D by it. Okay, just so we can keep track. And R sub D is, once again, 7 ohms, like this, all right? And then that current can continue to flow. So let me draw more of the circuit, all right? And they don't have to be exactly one on top of the other. So that's R sub C. And recall R sub C was 5 ohms. So I don't want to mess any of the writings up. Okay, then you've got another resistor. All right, and let's put this guy all the way at this end over here, and that resistor is a 4 ohm, and it's called R sub B. So R sub B is equal to 4 ohms, and it's all the way back there. And the last one, let's just kind of zoom out a little bit and take this picture and move it down, just so that I have enough space to draw this last one. And that last one is, so when you're working with these, guys, just remember, draw them really spaced apart so you can work with your calculations and stuff like that as you go through them. There you go. I'll draw that one right there, and I'll call that R sub A. And again, R sub A is 2 ohms. Okay? All right. Now what we're going to do is, and again, this battery is a 9-volt battery. All right? So now what we're going to do is we're going to run through the same exact steps as we did earlier, just a little bit quicker because the lesson has gone on for very long, right? So we're going to run through the same exact steps. The first thing that we need to do is we need to find equivalent resistance. Okay, so step 1 is we need to find Req. Now, how is Req found in this situation? Basically what you do, the formula looks like the following, and I'll explain it to you in a moment. I know it looks kind of crazy, but in your calculator I'll show you how that can be done all in one go. It's basically the reciprocal, okay, it's the reciprocal of the addition of the reciprocals. If you're a math person, which many of you are, right? It's the reciprocal of the addition of the reciprocals. That's how you get that, that resistance. And what's really neat is the voltage that's felt across. We'll come to this in a little bit. That's rule number 2. All right, so this is rule number 1. This is rule number 2. The voltage that's felt across each one of them, the drop, is going to be the same. So you're not going to have to spend too much time figuring out the drop, all right? Now, let's go ahead and figure out the equivalent resistance. So let's write it down first. So the equivalent resistance is going to be 1 divided by, oh, I have a thing for straight lines, so it needs to be a straight line. So 1 over R sub A plus 1 over R sub B plus 1 over R sub C plus 1 over R sub D, like that. Okay, so you're going to find that equivalent resistance. And I'm just going to take a calculator right quick, and I'm just going to push it into a calculator, and it'll do all of that work for me. All right, so let me just come here. All right, clear this. All right, so in our calculator, what you want to basically do is you want to take all of those numbers that you're looking at and do 1 divided by, all right? And then you want to make a set of parentheses so you don't get confused between them. And then 1 divided by R sub A. So this was 2, 4, 5, and 7 in that order. So I'm just going to go ahead and put those in. So 1 divided by 2 plus 1 divided by 4 plus 1 divided by 5 plus 1 divided by 7, like that. So notice how I had opened a parenthesis all the way at the beginning, so I want to make sure that I close that parenthesis in as well, even though it looks like it wasn't that necessary to have that parenthesis. So there you go. I've got an equivalent resistance that actually runs through this entire circuit over here. All right, so I'm going to write down 0.915 ohms is the equivalent resistance that is running through that circuit. All right, that's step number 1. So notice how the problem begins the same in either way. You have to find the equivalent resistance, right? Why it took us longer in that last one is because I had to explain to you how current flows at the same time, right? So now, in step number 2, you need to go ahead and use Ohm's law. Okay, you're going to use Ohm's law, and you're going to find that total. I'm going to put T over here. You're going to find the total current by taking the equivalent resistance. So notice you couldn't get to this step if you hadn't done the previous one. So the voltage of the battery is still the same. All right, the voltage that it pushes is 9 volts. All right, and you're dividing that by 0.915 ohms. All right, and the answer is back in amperes. So let's go ahead and do that. 9 divided by 0.915 is going to give us 9.836 amperes. So 9.836 amperes. So what we're going to do, because we're going to have to put these in a calculation, let's just go ahead and turn that into 9.8 amperes. Okay, so 9.8 amperes, that's the total current running through them. Now, you figured out as much of the standard of the lesson is that's really where it's going, but you need a little bit more than that for your future. So we're going to go through now how exactly does current flow through this, and you are responsible for it then. Okay, so don't think that this is something that's optional. All right, so now current is flowing, we understand, through this wire. Okay, let me just draw the arrows on here. So that's the total current. All right, how much was the total current? The total current was 9.8 amperes. So there's 9.8 amperes of current that flows. Notice at this first juncture, what happens is the current is going to split. All right, the current splits. And when the current splits, part of it is going to continue on in that pathway, if you want to call it that, and part of it is going to run through that resistor. And then like this, what you find happening is the current, all right, the current is going to continue in this pathway, like this over here. Now you might be thinking, well, is it going to go ahead and split the other way? No, it's not going to split the other way. It's basically going to now come back to the battery like this over here. All right, that current. But then realize that there was a certain amount of current that did continue. So again, the current, whatever was left over, it's going to split again. All right, this current is going to split again. And when it splits this time, there's a certain part that's going to go this way. It's a certain amount. All right, we'll calculate that in a little bit. It depends really on the resistor, and it's going to come back down through the battery. Okay, then it's going to split here, but you get the idea. It's going to come back through here like this, like that over there, and it's going to cut through here as well. So now I have labeled for you, and you don't have to make this many arrows. I'm just trying to help you understand the flow of current. Remember, it goes through the positive terminal, all right? The conventional current flows out through the positive, comes back in through the negative, even though electrons flow the other way, if you really think about it. Okay, now, what we're going to do is we're going to make that connection, and this is where rule number 2 comes in really handy. It says whenever you have a circuit and the resistors are all in parallel to one another, the moment that you get that, the voltage is equal. The voltage that is felt across each one of those resistors is equal. Now let me pause here, and this is a very important juncture. Realize that in that previous one, our foot in through the door, is we had said that the current through every single one of those resistors was equal. So then what we had done is we said, well, if the current is equal through each one of these resistors, then I had begun with the green, and I said each one of these is going to receive the same amount of current. And that helped me with the I and the R that I had to figure out the V, right? So what I'm trying to say now is in a resistor in parallel, you now know that the voltages are the same, right? So that again is going to help you, but this time it's going to help you figure out the current that runs through every single one of these. So what we're going to do is we're going to go to every single one of these, and we're going to mark down how much voltage is going through them. Now, if you realize if there's a 9-volt battery, and we're saying that the voltage that runs through them is exactly the same, so what we're really trying to imply here is the following. We're going to put it in green, that the voltage drop across D is going to be 9 volts. All right, it's going to be 9 volts right there. The voltage drop across resistor C is 9 volts. Resistor B, 9 volts. And resistor A, 9 volts. All right, you'll get used to all those subnotations. Takes a lot of practice, but you'll get used to them, okay? Now, you might be saying, wait a minute, aren't you going to run out of voltage if you're going to do something like that? So that's what you really need to understand in a parallel circuit. That's just how it works. The battery is directly paired up with each one of these bulbs. Just think about it that way. And so it receives, when all of those charges, they go up here, this is a high plateau, okay? And then they all drop at the same time basically, and they go through, and then they all come back at a low state. And that's why they have no reason to go turning around and going the other way. They just want to go back to the battery, right? They just want to go back to the battery to get recharged and get pushed up again. So the voltage drop across each one of these is going to be 9 volts. So what that's going to help you is you can now use, so let's label this as a step. So now you can use Ohm's law once again, and this time you can use it to find the current that works through every single one of these resistors, because the current is not the same through every resistor because they are in parallel now. So let's figure out the current that is going through. Let's do it in the color blue. So IA is equal to VA over RA. All right, so the voltage divided by the resistance. And so that's an easy one to do. That's 4.5 amperes. All right, that's the 4.5 amperes that runs through there. Okay, now let's take a look at the next one. Let's take a look at the next one. The next one, same exact idea, so I won't write the work, but take V and divide by B, and I believe 9 divided by 4 is 2.25 amperes. So that's how much current runs through that one. All right, third one, IC. 9 divided by 5, I believe, is 1.8. You can check me on that. I may be wrong. So that's 1.8 amperes. And finally, 9 divided by 7. I'm totally caught on that one. I do not know. So 9 divided by 7 is 1.28. So the current through D is going to be 1.28 amperes. All right. Now, notice that at the end of the day, all right, at the end of the day, what we were talking about is a total current of 9.8 amperes, right? 9.8 amperes. So if you were to take the current that is running through each one of them, because we did say that the current splits, right? Meaning it has the ability to come back together again. It's going to rejoin. So by the time it comes over here, right? By the time it's over here, let's suppose it should current should be completely rejoined. Current is completely rejoined. My struggles with spelling continue. All right. So if you were to take 4.5 and add it to 2.25, you end up with 6.75. Now add that to 1.8 and add that to 1.28, you'll realize that that current is still conserved. It's the same amount of current that comes back through the battery right there. Okay, so the last thing that you would need to do in this is to figure out the power that each bulb feels. So power is equal to the current times the voltage, recall? And so the current running through it is 4.5, and the voltage running it through it is 9. So 4.5 multiplied by 9 is going to give you 40.5 watts. So you got 40.5 watts that are running through this. Now I want you to realize something, and you're welcome to solve for the other ones, and I want you to solve for the other ones. So find power B, find power C, find power D. You want to realize something here is notice that the one that has the least amount of resistance has a lot of power that is running through it. Okay? If you go to the next one, PB is equal to IV, right? So IB times VB. And so that's 2.25 times 9. So 2.25 times 9. And now you get 20.25 watts. Right, like that, right? So the one that's got more resistance is actually going to have what? It's going to have less power. And when it's going to have less power, this one is going to be less bright. It's not going to be very bright. The other one is going to be more bright. All right? So like that, you can continue through this, and you'll notice that all of a sudden the wattage through these bulbs, what was it initially looking like 0.5 watts, right, on A, is actually 40 watts on A. You see that? Because of the fact that the voltage from that battery goes straight to that bulb over there. Now, if you're wondering, well, why would you ever even bother to wire things in series? Well, parallel definitely seems like the way to go, but in series, sometimes you want things to break like this. You want that if one of them fails, you want the rest to fail. But the lesson has gone long enough, so I don't want to continue with that for too long. One last thing I will tell you is we somewhat use this third rule, and it's called the junction rule. And the junction rule basically says that that current is going to be conserved. Okay, what's going to go in is going to come back out again. So what went in was 9.8 amperes, and what came out at the end, as I showed you with this arrow over here, is 9.8 amperes. So it is what came back out again. All right. But again, the rule number 3 in both situations, it'll really be handled in the next lesson, which is honestly, it's a very interesting lesson. It's a very good lesson when we have to solve circuits that contain both of these situations. Well, thank you for listening, and good luck on the homework. All right. Feel free to reach out if you get stuck on it, inshallah. I will try to give you extra amount of days to do it. And Assalamu alaikum.